Welcome to A Visual Approach to Optics, a guide for clinicians, narrated by Dr. John Gorfinkel. This is the 5th episode. We finished 107 out of 277 slides in the previous episode. In the last episode, we finished with the slide on conoid of Sturm, where we see that a lens that has different power in different axes results in a conoid of light that never quite compresses to a point. However, it compresses into a line, and a line at right angles to the first line at different distances. In between, the cross-section of this conoid looks like a circle, which is called the circle of least confusion. If one is to choose which point on the conoid is the best to put on an image plane, the answer would be the circle of least confusion. Here we see a situation of two equal cylinders at 90 degrees to each other. This results in a refraction equal to that of a spherical lens in which light in all axes is focused to a point. The same is true of a minus lens, which forms a virtual image point. Here we see the notation that we use. There are two ways to describe this. We can describe it as two cylinders shown as +2 diopters with long axis at 180 degrees together with +2 diopters with long axis at 90 degrees. Or we can just write it as +2, in which case it indicates a sphere. In the case of the minus lens, everything is similar, but with minus signs. Here we see two cylinders of unequal magnitude, one horizontal and one vertical. Note that the long axis of the +2 cylinder is horizontal. However, the power is in the vertical axis, because that is the axis with the curved surface. In the case of the cylinder with long axis that is vertical, the power is horizontal. We can show the notation of the cylinder axis by the orientation of the long axis of the cylinder. In this case, we write +2 at 180 degrees or +350 at 90 degrees. However, note that the power is at right angles to the axis notation. In other words, the power is +3.5 at 180 and +2 at 90. We draw power cross diagrams to indicate this. The vertical meridian has +2 power, and the horizontal meridian has +3 power. Regardless of the axis of the power, we write cylinders describing the long axis of the cylinder, which is at right angles to the maximum power. So in this case, we would write +2 at 180 degrees and +3.5 at 90 degrees. This notation is called the two-cylinder notation form. We can also describe cylinders as spherocylindrical combinations. In this case, what we previously described as two cylinders, the two-cylinder notation form here, we can also describe as a 2-diopter sphere with an extra 1.5 diopters in the vertical axis. In this case, we would write +2 for the sphere, +1.5 at 90 degrees for the long axis of the additional cylinder. This is equivalent to the two-cylinder notation here. The reason we use spherocylindrical notation is historical, because at one time it was easier to produce a spherical lens and glue on an additional cylindrical lens. Today the lenses are ground as a single unit. Here we see the minus spherocylindrical form. We take a sphere equal to the higher power plus cylinder of +3.5 and then deduct 1.5 in the horizontal axis to get +2 in that axis. So we have plus 3.5 minus 1.5 at 180 degrees. This is equivalent to the plus spherocylindrical notation, which is plus 2 plus 1.5 at 90 degrees. And this is also equivalent to the two-cylinder notation here. So here is a summary slide for cylinder notation. We have a plus 2 cylinder at 180 degrees and a plus 3 cylinder at 90. The power diagram shows the numbers reversed because the power is at right angles to the long axis of the cylinders. When writing the lens prescription above, we use the long axis of the cylinder. This is the two-cylinder notation, plus 2 at 180 with plus 3 at 90. The plus spherocylindrical notation, plus 2 sphere plus 1 at 90 degrees cylinder, plus 3 sphere minus 1 at 180 degrees cylinder. All three are different ways of describing the same combination. Here we describe how we would correct a astigmatic error of the eye with a correcting cylinder. In this case, we see a minus 3 diopter cylinder eye error. The eye is deficient in this amount in the 90-degree axis of the long axis of the cylinder, which prevents clear vision. We can put a cylinder of opposite sign parallel to the original eye error in front of the eye in order to neutralize it. We would describe this as a plano, which is 0 sphere plus 3 diopter cylinder at 90 degrees. We can also think of this as correcting this same eye error with a plus 3 diopter sphere and a minus 3 diopter cylinder at 180 degrees. The reason this works is because we are taking this minus cylinder and putting it in front of another minus cylinder at right angles, which then creates a minus 3 diopter sphere effect, and then this is compensated for with the plus 3 diopter sphere put in front of the eye. We write this as plus 3 sphere minus 3 cylinder at 180 degrees. These two notations are mathematically equivalent, and a lens ground as a single piece in today's world would be the same either way. Here we see what happens when the eye has corneal astigmatism. The power in the vertical meridian is lower than in the horizontal. We show 42 diopter power vertically and 44 horizontally. This combination of cylinders would result in a conoid of Sturm. We show the conoid of Sturm here centered on the retina such that the circle of least confusion is on the retina. Here we show the vertical line anterior and horizontal line posterior. In actual fact, the back half of this conoid of Sturm would not really exist because light would not get past the retina. In other words, only the anterior part of the conoid exists in space, and it happens to intersect the retina, in this case, at this circle of least confusion. If the conoid happened to intersect the retina closer to where the vertical line is, we would have had vertical ovals on the retina. Or if it had intersected closer to the horizontal line, we would have had horizontal ovals on the retina. Here we show a few types of astigmatism. In compound myopic astigmatism, the vertical and horizontal lines are shown in front of the retina. The two lines and the circle of least confusion are both in front of the retina, and the part of the conoid behind the horizontal line, which would be a horizontal oval, intersects with the retina, and this is what the retina would see. In this case of simple myopic astigmatism, the conoid is shown where one of the lines is on the retina and the rest of the conoid is in front of it. In other words, the retina would see a horizontal line. In compound hyperopic astigmatism, both lines are behind the retina, as is the circle of least confusion. The only part of the conoid that would intersect the retina would be near the vertical line, which would actually be a vertical oval. The retina would therefore see a vertical oval. In the real world, none of this part of the conoid would exist because light would not get behind the retina. It is just shown to indicate what the light would have looked like if it could continue. In this case of simple hyperopic astigmatism, the vertical line is shown on the retina and the rest of the conoid behind it. Again, the rest of the conoid would not exist because the light would not cross the retina. The retina would see a vertical line in this case. In mixed astigmatism, the two lines are on opposite sides of the retina. The circle of least confusion may be on the retina or may be on either side of it. But the key to mixed astigmatism is that the two lines of the conoid are on different sides of the retina. In the real world, only the part of the conoid up to and including the retina and in front of it would exist. The back half would not, because light would not get there. This is just to indicate the overall optical situation. Here we show corneal astigmatism and how it can be represented by cylinders. We have a vertical power of 42 and a horizontal power of 44 in this case. We can consider the vertical power of 42 as a horizontal cylinder, long axis horizontal, with a vertical power of 42 diopters. We can consider the 44 diopter horizontal power part of a 44 diopter cylinder with long axis vertical, and the horizontal axis therefore has 44 diopters of power. The higher power cylinder, which is vertical here, would create its corresponding line, in this case vertical, in front of the line of the other cylinder, which is shown here, the horizontal line, further back. In this particular depiction, we show the conoid intersecting the retina at the circle of least confusion. However, different refractive numbers could result in any part of the conoid intersecting the retina. Either vertical ovals here, the vertical line, vertical ovals, the circle, horizontal ovals here, horizontal line, or horizontal ovals here, depending on which part of the conoid would intersect the retina. Here we show with the rule astigmatism. One can think of this in one of two ways. The first way is to consider that the vertical meridian has higher power. That is one definition. Another way of thinking of it is as an embedded cylinder with horizontal axis plus cylinder in the cornea. A horizontal plus cylinder would have a vertical power, which is the definition of, with the rule, astigmatism. We can correct this astigmatism by using another horizontal cylinder in front of the eye, which has the same but opposite sign power. The other way is to use the same sign cylinder, a plus cylinder of equal power, at right angles to the first one, and then we need to offset with a minus sphere, as seen earlier. shown here is against the rule of astigmatism, which is higher corneal power in the horizontal meridian. This is as if there is a plus cylinder embedded in the cornea, long axis is vertical, such that the power is horizontal. We can correct this vertical plus cylinder with a vertical minus cylinder in front of the eye, or another plus cylinder that is horizontal, which converts the overall error to a sphere and then offset with a minus sphere. If we decided to correct this eye with different power spheres in front of the eye, we would be able to move this conoid back and forth. But we would not be able to collapse the conoid. Only by correcting the cylinder within this optical system can we collapse this conoid to form an image point. Astigmatism can be created by either surgical procedures or masses that press on the peripheral cornea. In this case, we show a corneal profile here with a horizontal power and a vertical power. If we put sutures in, as shown in the 90-degree meridian, that flatten the peripheral cornea, it forces a steepening of the central cornea in the vertical axis. Here we see a fixed chord length that is flattened peripherally and therefore forces a steepening in the central area. A steeper vertical meridian is like having a horizontal plus cylinder embedded in the cornea, which is therefore with the rule astigmatism. Similarly, a mass under the upper lid that has a weight to it can also flatten the peripheral cornea superiorly and cause a similar astigmatism. Here we see an object at infinity that is being refracted by this lens with 3 diopters vertical cylinder and 5 diopters horizontal cylinder. Because this lens does not have the same cylinder in every axis, this is an astigmatic lens that will result in a conoid of Sturm. The higher power horizontal cylinder will create a corresponding line 1/5 meter behind. This is 5 diopters in this axis, and there is the line behind it 1/5 of a meter away. The vertical cylinder here is plus 3 diopters and would create its vertical line, corresponding line, 1/3 of a meter behind it. If one takes the average of 3 and 5, one has a spherical equivalent of 4, which means that the circle of least confusion would be created 1/4 meter behind this lens. In other words, the circle of least confusion is not halfway between the two lines, but is halfway dioptrically at 4 diopters, which is halfway between 3 and 5. We get the spherical equivalent of an astigmatic lens by taking the average of the two cylinders. In this case, the average of 3 and 5 is 4. We can also use the spherocylindrical notation, as here, in which case we take the sphere and half of the cylinder, in this case 3 plus half of 2, which also gives 4. If we now assume that this astigmatism is part of the corneal power, and we wanted to correct this patient's eye, we could try two things. If we tried to put different spheres in front of this, we could move the conoid of Sturm back and forth and try to find an optimal point over the retina, but we would not eliminate this conoid of Sturm. Only by putting an astigmatic lens in front that was equal and opposite to the one here would we be able to collapse this conoid to a point. In other words, it is better to correct astigmatism with astigmatic lenses than with spherical equivalent. We can correct corneal astigmatism with contact lenses. We can use, in this case, is shown a rigid contact lens. It basically replaces the corneal surface with another new surface, and the intervening space is filled with a tear film that has much more similar index of refraction to the cornea and the contact lens than air. One can think of this as a new spherical surface given by the rigid contact lens, or one can think of it as correcting the astigmatism by having a different width of the tear film under the contact lens in different axes. It is mathematically equivalent either way. In this case, we're showing an eye with against the rule astigmatism because the horizontal power is 44, which is higher than the vertical. Therefore, if the horizontal power is the higher one, it's as if we have a vertical 44 diopter plus cylinder embedded in the cornea, and a horizontal 42 diopter plus cylinder. Here we show irregular astigmatism with a very irregularly shaped cornea, which would cause significant aberration. It is best corrected with a new corneal surface formed by a rigid contact lens. There are no glasses that would effectively do the job because of the aberration. However, with a new corneal surface, or virtual new corneal surface with the contact lens shown here, the tear film fills in all the irregular spaces behind it, thereby neutralizing the aberration. Here we see a myopic eye being corrected with a rigid contact lens. We have just made sure that the contact lens has a curvature that's flatter than that of the cornea. Because the curvature is flatter, in other words, the radius of curvature is larger, the power will be lower, and thereby allow the image to be formed further back towards the retina. Here we show a hyperopic eye in which we've corrected the eye with a steeper contact lens. It is steeper than the curvature of the cornea. In other words, the radius of curvature is smaller so that the power is greater, and it allows the image to be formed more anteriorly so that it can be on the retina in the hyperopic eye. Note that the tear film fills in the spaces between the two surfaces. We can also use soft contact lenses which mold to the shape of the cornea rather than have their own rigid shape. In this case, we then have to have a lens ground into the soft contact lens to give the effect. In other words, in this case, if the posterior surface matches that of the cornea, it is not neutralizing any power, but the anterior surface of the contact lens here is shown to be flatter than the posterior surface, and thereby allows the power overall of the front here of the eye to be lower, and therefore the image can be focused further back. Similarly, in the hyperopic eye, we have a contact lens where the posterior surface matches that of the cornea because it is soft and drapes itself over the cornea, but the anterior surface of this contact lens is more curved, and this allows a greater overall power, and thereby moving the image more anteriorly in this hyperopic eye to get a better result. In the soft contact lenses, the tear film does not play a role because it is only the anterior surface curvature that does the job. In the case of rigid contact lenses, one can think of it as similarly the anterior surface doing the job or the intervening tear film between the two surfaces, which is mathematically equivalent. Here we show laser vision correction in which the surface curvature of the cornea is reshaped by an excimer laser. Here we show the original surface curvature, and here we show the final one. The final one is flatter and therefore weakens the power of the cornea and allows the image to be formed further back in this myopic eye. Note that there's a thinner cornea after the procedure in the center. In this patient, corrected for hyperopia, the cornea is reshaped from its original, shown in the red dotted line, to be thinner, more peripherally than it is centrally, and thereby increasing the overall curvature of this new surface. This increases the power of the cornea and allows the image to be focused more anteriorly in this hyperopic eye. Astigmatism will cause blurring of different degrees in different axes. Here we show uncorrected astigmatism in which some letters are more affected than others. These are the original letters, and this is how it would look if the image were more blurred in the vertical direction than in the horizontal. Say, the portion of the conoid that intersects the retina would be a vertical oval or vertical line, for example. In this case, the letter I is not affected very much because the vertical blurring of all the points that make up the letter I overlap so that the overall shape is still preserved. In this case, we show the letter E, which depends on horizontal parts. These are then smeared vertically by this astigmatism so that the vertical lines here, or the vertical line here, is preserved, but the horizontal lines are severely reduced. So in this case, in this particular example of astigmatism, one can see the letter E is more affected than the letter I. For purposes of clinical testing, we can use different letters and get a reasonable result, but for research purposes, it is important to use the same type of letter in different orientations, say the letter E, for example, or the letter C, in order to avoid this inconsistency. Here we see the effect of an aperture on light. If we take divergent light and use a very small pinhole, it is possible to form an image point, or approximate an image point. However, the overall image would be very low intensity. We can also pinhole light in one axis only, in the sense that we reduce what would otherwise be an overall divergent blur of light into a single line. It is not as good as an image point, but it's still better than no aperture. This vertical aperture is known as a stenopeic slit and is seen in many animals that have pupils of this shape. We are now moving to Chapter 3. We have finished Chapter 2, Geometrical Optics, and are now going to prisms and prismatic effect of lenses. Here we see a prism. This glass prism has a flat surface that is at an angle from its second surface and is connected at the bottom. We have an object with divergent rays which are being bent according to Snell's law as it crosses the boundary on this side from air to glass. The rays are bent towards the normal, and on this side, when exiting the glass, the rays are bent away from the normal. The overall effect is to change the direction of the rays that appear to be coming from an image higher up than the object to an observer on the right. Note that the divergence of the rays is not different, just the direction of them is different. In other words, the virtual image is in the same plane as the object, but at a different location. This shift in image is called prismatic shift. Here we see the definition of a prism diopter. If we have an object that's very far away, we're only showing the central ray of the object. It will cross through the first axis here at right angles without deviation, but here it reaches the normal of the surface at an angle and therefore will be bent according to Snell's law. When going from higher index of refraction to lower index, it is bent away from the normal. The normal is at 90 degrees to this surface, therefore this ray is bent away. So whereas the object came from here, to an observer on this side, it appears to have come from up here. When we have an object 1 meter away, and it is deviated by a certain number of centimeters, we call that a prism diopter. Here, one shows a greater deviation than here. In other words, x centimeter is a larger number here than it is here at 1 meter away. Note that as the angle increases more and more and approaches 90 degrees, this direction showing x centimeters gets increasingly non-linearly larger until it reaches infinity. In this way, the prism diopter is an odd way of describing this. Using the angle here would have been better, but historically, this is what has taken hold.